So before we get to some real problems here, there's some more stuff we need to talk about, more things that we will use in proofs. So these three things here, we've already discussed. We talked about these in the very first chapter of the year. Okay, but now we're actually going to have to refer to them by their names whenever we do proofs now. Okay, so the first thing here, in your notes, it says the sum of the lengths of two adjacent segments is equal to the length of the whole segment. And that was nothing more than the segment addition postulate. This is where we took one little segment and we added another little segment to them, stuck them together, and we really made a bigger segment. Okay, so you can think of the segment addition postulate as little segment plus little segment equals big segment. Likewise, we also have the angle addition postulate, which was like the same thing as the segment addition postulate, except we did it with angles. So we had little angle plus another little angle that's adjacent to it that's side by side, and together they add up to make a bigger angle. Okay, no surprise there. But now we need to refer to it as the angle addition postulate. The last thing is whenever, it's kind of like the angle addition postulate, but it's when our big angle is really a straight line or a straight angle. And so any number of angles using the same vertex that make a straight angle or a line add up to be 180 degrees. So we're going to use the straight angle postulate. This is kind of like a special case of the angle addition postulate when they equal 180 altogether. Now this doesn't have to be supplementary. This could be any number of angles. So let me just show you real quick what I mean by that. Say here's a straight line, here's a vertex. Well, if I get my pen working here, there we go. There's a vertex. And so I could have, say, just two angles, 1 and 2. And what do 1 and 2 add up to be? They add up to be 180 because together they make this straight line. And technically 1 and 2 are called supplementary angles because it's two angles that add up to be 180. But now, what if I just throw in an extra ray here? We'll just say right here. Well, now I've got three angles, but all three of these angles put together still equal 180 degrees. But now I can't call angles 1, 2, and 3 supplementary because by definition supplementary was two and only two angles that had to be 180. All right. Now a very common misconception is, let me extend this guy here, be a little bit longer, is if I have multiple vertices on the same line. Let's say I have three vertices. Let's make this one have lots of rays coming out from that one vertex. And let's just have this one have one. And let me make this guy just a smidge bit longer. Okay, so if I had angles 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, some people would look at this and go, hey, this is one straight line. It has only 180 degrees in it. Not quite. There's really infinitely many degrees on any line. It just depends on where you look on that line. Okay, so just imagine we're only looking at this part of the line. With that one vertex, this is 180 degrees right here. Likewise, if we just looked at that part right there, then angles 4, 5, 6, 7, 8, 9, and 10, they all add up to be 180 because they use the same vertex. And angles 11 and 12 add up to be 180. But some people might look at this and go, well, angles 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 all have to equal 180 because they're all on the same line. Well, but they all use different vertices, different vertexes there. Okay, so that's the main difference. Each of these three sets is 180 degrees by themselves, not all together. Now, in addition to postulates and properties, we will use some definitions. Okay, sometimes we'll be given a vocabulary word, and we need to define what that means, either mathematically, or we might have a mathematical version, and we need to define what that word is, kind of like backwards, looking up, if you knew the definition of a word, and it would give you the word that definition describes. So definitions can go both ways. You got the word, you got the definition. If you know the definition, you can apply it to the word. So angle bisector, midpoint, right angle, complementary, supplementary angles, and perpendicular. These are all things that we have talked about before. An angle bisector is just cutting an angle into two congruent smaller angles. A midpoint is the point halfway on a segment that cuts the segment into two smaller congruent segments. Okay, it's the halfway point. A right angle, well, that's exactly 90 degrees. Okay, you're thinking, well, do we really need to know the definition of a right angle? You'll see when we get to some specific examples. Complementary, supplementary, we've talked about those before. And perpendicular, keep in mind our little symbol here, the upside down capital T, just means that we have segments that form a right angle. And a right angle means we have 90 degrees. So we will use these throughout the chapter. Okay, so just hold tight now. So let's do a couple of examples together where we're going to have to use this stuff. Okay. So this says if dt, and that's all of this, if that's equal to 60, then solve for x and justify each step. So we're going to do a proof, but now we're going to start mixing in some geometry with the algebra. Okay? The first thing we're going to need to do is set up the geometry part of this. All right, so if I've got a little segment here and another little segment, ds and st, and altogether that makes a big segment. There was something we talked about earlier. What was that exactly? It was on this page, but I need to do this. Oh, well, that was the segment addition postulate. So here's how I need to set this up. I don't automatically get to jump in and say 2x minus 8 plus 3x minus 12 equals 60. I got to start with the pure geometry part of this. So my first step would be to say, all right, well, segment ds plus segment st should equal segment dt. And why do I know this is true? Well, I know this is true because my pen would work very well here. I'm going to abbreviate some stuff here. The segment addition postulate. The segment addition postulate tells me I can do this based on this picture. All right, so now that I've got this, now I can start implementing the algebra into this. So once I've got this, well, ds. Well, what's ds equal to? Oh, well, ds is equal to nothing more than 2x minus 8. Okay. And st, what's st equal to? Well, it's equal to 3x minus 12. And dt, what's dt equal to? Well, they told me up above in the beginning that dt is equal to 60. Why can I do this? Why can I take values and plug them into other things that are equal to each other? Well, what other property did we use here? It's none of these. Man, we might need to go back and look at some older stuff. Oh, hey, what about this guy, the substitution property of equality? So let's fast forward. So here we used the substitution. Oh, and I can just say PE. We can shorten it up there instead of saying property of equality. So I've substituted my values in from my geometric stuff. And now from here, it's nothing more than the algebra problem. All right, so now I need to look over here. We need to combine some like terms. Let's see, we've got 5x and minus 20 equals 60. All right, what was that step called where we added like terms? I believe that step was called just simplifying. And then from here, what would I do? Well, I would want to add 20 to both sides. So if I add 20 to both sides, that 60 is going to turn into an 80. And if I add 20 to both sides, well, that's the addition property of equality. And now if I want to get x all by itself, because that's what I need to solve for up here, I would divide the 5 over. So if I divide 5 over, 80 divided by 5 is 16. And I divided both sides, so I used the division property of equality. I have gotten to the very end of this problem, so now I know that x equals 16, and I'm done, so I'm done with that proof. All right, the next example we're going to look at, same type of thing. We're going to set it up geometrically and then transition it to the algebra problem. All right, so given C is the midpoint, all right, there's C, apparently it's the midpoint of AB, so it's right in the middle of this. Calculate X and justify each step. Okay, so if C is the midpoint, that really means that this piece over here, AC, is the same thing as this piece over here, CB. So really, I'm just going to set these two things equal, and now let's do the algebra. Not quite. But that's the idea we want to do here. So knowing that this piece of information is true, we're going to come down here and say, all right, well, if that's true, then what we can conclude is that segment AC is really equal to segment CB or BC. And why do we know that? Well, there was a particular word up here called the midpoint. And what does midpoint mean? Well, it means that we can do this. We can set these two pieces equal to each other. So we just used the definition of midpoint and applied it to this problem. And this is what we can conclude it based on the definition of a midpoint. So now here's where we need to make the transition now between geometry and algebra. And that transition is through the substitution property. So AC, that's 2x plus 1. CB, that's our 3x minus 4. We use the substitution property of equality. All right, and now let's just do the algebra. Well, let's see. We need to subtract 2x over. And so if I subtract 2x on both sides, I just have the 1 left there, and 3x minus 2x would just be x, or 1x, and I'd still have the minus 4. So I use the subtraction property of equality. And then I would need to add the 4 over, and if I added the 4 over, that would turn into a 5. And so I use the addition property of equality, and I've got x now. X equals 5, or 5 equals x. It doesn't really matter. Here's where, and this is really silly, but if you really wanted to, if it bugs you that x isn't on that left side, this is where you could say, all right, I'm now going to write it as x equals 5. Well, how do I know that this is really true? Well, if 5 equals x and x equals 5, that's where we could use the symmetric property of equality. Again, I would stop right here. I am fine with 5 equals x. I can read that backwards and say, hey, yeah, that's x equals 5. If it bugs you, then you have to do this extra step, okay? But this is purely optional. Only if it bugs you that x isn't on the left side. All right, the last problem. I want you guys to try this one on your own, okay? If you followed along with the first two, this one I would think, it just involves angles now instead of segments, that it should flow very similar to the previous two. First, you need to set it up geometrically, talking about the specific angles here, and then transition to the algebra through the substitution property. Now, I don't want you to go the whole way, just like we did on the previous two. What I want you to do is just to stop, because I know you guys can do your algebra. Stop when you get to the algebra solving part of this. So for example, if we were doing this one, I would just say stop right here. Because again, I know you guys can do the algebra solving aspect of this. If we were doing this problem, I would have told you to stop right after the substitution. So that's where I want you to stop on this problem here that I want you to do on your own. So we'll talk about this one tomorrow in class. We'll get it all set up. We'll solve it. We'll figure it all out.